Okay, we'll now do some exercises. First one, x s mu measure space, fn sequence of measurable functions converging uniformly to f, to a measurable function so let us write integrable functions. To an integrable function f. Yeah. So, is it necessary that integral fn d mu over x goes to integral over x f d mu? Solution: true if mu x is finite. I leave this as an assignment. Okay, so not necessarily true if mu x is plus infinity. So we have to give a counter example. So let us take x equal to r, Lebesgue measure. So fn is the function which is given like this. I'll draw the picture. You can so this is minus of n plus 1, this is minus n, this is n, and this is n plus 1. So the function is equal to 1 by n from minus n to n, and then goes to 0 here. Okay, so fn is a function with compact support, therefore fn is definitely integrable, and then fn mod fn is less than or equal to 1 by n, and therefore this implies that fn converges to 0 uniformly. But what about integral fn d mu? dm1, sorry. Now that is just it's a continuous function, and from our whatever we know it is greater than or equal to, for instance, integral over minus n to n fn dm1. But there it is a constant function, namely it is equal to 1 by n into 2n, which is the measure, which is 2. Therefore integral fn d mu is greater or equal to 2, but then, and therefore it does not converge to 0, and therefore this is not necessarily true. But if it's a finite measure space, then uniform convergence does imply the whatever this result is, and that's a very easy checking. Just apply the definition, you can do it like that. So second question, let f from R to R be Lebesgue integrable. Let t in R be fixed. Let define g of x is f of x plus t. You are translating the function. Let AB be contained in R. Show that integral over AB g dm1 equals integral of a plus t b plus t f dm1. So this is some kind of change of variable which we are doing in a very simple way. Okay, solution. So we are going to use that proof technique, namely prove it for characteristic functions, prove it for simple functions, prove it for non-negative functions, prove it for the integrable functions. Okay, so that's the idea we are going to. So let E contained in R, Lebesgue measurable, and let F equals chi of E. So G of X is F of T plus X, which is equal to chi E of T plus X, and that's equal to 1 if T plus X belongs to E, that is X belongs to E minus T, and 0 if X does not belong to E minus T. So this means that G is nothing but chi of E minus T. So what is integral over AB? G dm1 is equal to the measure of AB intersect chi of E minus T. But by translation invariance, this is equal to the measure of A plus T, B plus T intersection E by translation invariance. But that's equal to integral A plus T, B plus T of chi E dm1, which is equal to integral A plus T, B plus T of F dm1. So true for characteristic functions. Bilinearity true for simple functions. Then by monotone convergence theorem, true for non-negative functions, because every non-negative measurable function is the increasing limit of the of simple functions. So given any non-negative function f, you can take phi n increasing to f, phi n simple, non-negative, f is also non-negative. Then what can you, then of course phi n of x plus t will increase to f of x plus t. Okay, and then everything is true. Then by the monotone convergence theorem you can easily prove the result. And then true for integrable functions, because you take f equals f plus minus f minus. So you use this. So we all most of our work is there only for the functions which are characteristic functions. So 3 is called the differentiation under the integral sign. So let f be a function from 0 1 cross 0 1 to R. T in such that for every t fixed you have of course in 0 1 x going to f of x t is integrable. For every x in 0 1 fixed, t going to f of x t is continuously differentiable and the derivative with respect to t, which we define by df by dt of xt, is uniformly bounded. Show that d by dt of integral 0 1 f of xt dm1 with respect to x, because for each t this is an integrable function, and then this is equal to integral over 0 1 of df by dt xt dm1. That's integrable anyway because it is bounded. So you can take the derivative inside the integral sign. So solution. So let us look at this difference. So this is integral 0 1 f of x t plus h minus f of x t dm1. This is the difference quotient whose limit which will give you, if it exists, the d by dt here. So this is equal to, if you take the h inside, since it's continuously differentiable, this can be written as integral over 0 1. This difference quotient is df by dt of x t plus theta h dm1, where theta is between 0 and 1. Theta of course depends on x and t. So this is nothing but the mean value theorem. Now as h tends to 0, you have df by dt x t plus theta h goes to df by dt xt, continuity of the derivative. Okay, and mod df by dt x t plus theta h, this is less than or equal to m for all xt. Okay. Therefore, by the dominated convergence theorem, for any sequence hn going to 0, you can take the limit, and therefore you have limit h tending to 0 of 1 by h integral 0 1 f of x t plus h minus fx t dm1 equals integral 0 to 1 df by dt xt dt, and this therefore is nothing but d by dt of integral 0 to 1 f of xt dm1. Okay, so very nice application of the dominated convergence theorem to show that, you see, differentiation under the integral sign always requires some proof, and therefore this is one set of sufficient conditions which will tell you that you have this condition. For x s mu measure space, fn f measurable functions, and fn converges in measure to f. Mod fn less than or equal to g integrable for all n. Okay, show that integral over x mod fn minus f d mu tends to 0 as n tends to infinity. So this is the dominated convergence theorem. In the dominated convergence theorem, you have two parts. One is Fn goes to F almost everywhere, and Fn is bounded by an integrable function. What we are doing is replacing the convergence almost everywhere by convergence in measure, and even then the dominated convergence theorem is true. So solution. So I am going to use this technique. Namely, if I have a sequence such that every subsequence has a further subsequence which converges and the limit is independent of the subsequence, then the entire subsequence converges. So let Fnk be any subsequence. Then Fnk, of course, will also converge to F in measure. That's no problem. Implies there exists a further subsequence Fnkl which goes to F almost everywhere. Then by the dominated convergence theorem, you have integral mod Fnkl minus F d mu over x equal to 0. So for every subsequence, there is a further subsequence such that the limit is always 0, and therefore this implies that the entire sequence x mod Fn minus F d mu equals 0. So this is true for every subsequence Fnk. So you see how powerful that little observation about sequences is. Given any subsequence, there is a further subsequence such that the limit exists and the limit is independent of the subsequence. Here the limit is 0, which is independent of any subsequence you choose, and therefore the entire sequence converges. 5. Let F, so this is A, from 0 infinity to R be uniformly continuous and integrable. Show that f of x tends to 0 as x tends to infinity. So the function has to vanish at infinity. So solution. If not, then you can find an epsilon greater than 0 and Tn tending to infinity, and you can also take Tn minus Tn plus 1 to be bigger or equal to 1. So you can take it farther and farther away, okay, such that mod f of Tn is greater or equal to epsilon. Now f is uniformly continuous implies there exists a delta positive. Mod x minus y less than delta implies mod fx minus fy less than epsilon by 2. Then this will imply that for all y in t minus Tn minus delta, Tn plus delta, and we can choose delta less than 1, there is no problem. You can always choose a smaller this thing. We have mod f of y is therefore greater or equal to epsilon by 2, because its f of Tn is bigger than epsilon. In this neighborhood it is less than epsilon by 2, and therefore you have this is greater or equal to epsilon. But then integral mod f 0 infinity dm1 is greater or equal to sigma n equals 1 to infinity integral Tn minus delta Tn plus delta mod f dm1, and each one is the greater epsilon by 2, and then the length of the interval is constant, namely 2 delta. So you have epsilon by 2 into 2 delta. So each, this is greater to epsilon by 2 into 2 delta, which is equal to epsilon delta, which is a fixed number, and you have infinite number of them, and therefore this is plus infinity contradiction. So this is not possible, and therefore f has to go to 0. B, above not true if f is just continuous. So let us take, so we have to give an example. So let us take a function fn, f in the following fashion. So f is such that at each n you take n minus 1 by n square, n plus 1 by n square, and then it is, the function is height 1 here, and then it goes to 0 and 0 elsewhere. So this is for every n in n. So how does the function look like? So it looks like here is 1, and then here is 2, 3, and so on. So the function is like this. So this implies that f does not go to 0 fx as x tends to plus infinity. But what is the integral f dm? Once a non-negative function is nothing but sigma n equals 1 to infinity, the area of all these triangles, the height is 1, base is 1 by 2, height is 1, and 1 by 2 into height is 1, and base is 2 by n square, which is sigma 1 by n square, which we know is pi squared by 6, which is of course finite. Therefore f is integrable, but it does not vanish at infinity. So we will continue with the exercises next time.